All right, so polar form of a complex number. We're still dealing with radius and theta, r and theta, but now it's going to be representing a complex number. So it's similar to polar coordinates, but we have a little different characteristic with the complex number. So to review complex numbers, and I think a lot of people think it has to have an I in it to be a complex number, but 4 is a complex number, 0.5 is a complex number, 3i is a complex number, and then we can combine real numbers and imaginary numbers, and those are complex numbers. But that's still a complex number, and that's a complex number. So all the real numbers and all the imaginary numbers combined are the complex numbers. We have the real number plane. That would be where we have an x and a y, and we could have two real numbers, 3 and -4. So that's the real plane. And then we have the complex plane. And that's where we have a real number on the horizontal axis and an imaginary number on the vertical axis. And in this case, we could have 3 minus 4i. So this is a little different, where here we have a comma and two separate numbers. This is one complex number, and we graph that in the complex plane. So this represents one number, this represents two different numbers in the real plane. All right, the absolute value of a complex number is just going to be the radius going to that point in the complex plane. So we'll go 1, 2, 3, 1, 2, 3, 4, 5, 6. There's the graph of that complex number on the real axis and the imaginary axis. To find the absolute value, we can write, that's the notation for absolute value, and all we're going to do is use the Pythagorean theorem. So if we just need to find that length. So if we looked at the triangle, and we can then see why we're going to square each of the numbers. We don't square the I. If we squared the I, we'd have a negative, and that wouldn't be representing what we want in the graph. We just want that length, so we go 3 squared plus 6 squared square root. Take out a 9, and 3 radical 5 is the length of the hypotenuse in that graph. And okay, you try the other one. Pause the video. Between 2 and 3. So we're going to go up little bit between 2 and 3, over 3, up to and some fraction. That will be the location of that complex number, and the absolute value is going to be 3 squared plus radical 5 squared. We don't include the I. So there's the absolute value of the complex number. All right, and polar form of a complex number. We are going to talk about a location in the plane. Just like we did with polar coordinates, we can talk about this location as being a radius and theta. And when we do that, we can represent the complex number as a radius times cosine theta and I times a radius times sine theta. It's the same, it comes from or is related to x equals r cosine theta, y equals r sine theta. We saw this with polar coordinates, and if we want a vertical distance, we just go r sine theta. If we want a horizontal distance, we'll go r cosine theta. The I is just has to be there because we're talking about a complex number. All right. So like we did with polar coordinates, we need to have an R. In this case, that's the absolute value. And we need to have theta. Absolute value and theta. So the absolute value is going to be 4 squared plus negative radical 2 squared and theta is just inverse tangent of the vertical value, negative radical 2, over the horizontal value. We saw that with polar coordinates, y over x. So theta is approximately negative 19.47 degrees. And if we're going to write that in polar form, we'll have z equals r cosine negative 19.47 plus I sine negative 19.47. Okay, and you try that one. So we'll find we need the absolute value and theta. The absolute value is squaring both components and then square root. theta is the inverse tangent of the vertical over the horizontal. So the polar form, we have the standard form and now polar form. Z is R cosine theta plus I sine theta. Nope, it's not going to be 60. Let's take a look at the graph. Inverse tangent will only give us an angle between negative 90 and 90. But look at this number is in the third quadrant. So we'll be over here. If we have a 60 here, then to get over to where we want to be, we have to add 180. So 60 plus 180 is 240. So instead of being at 60, we're going to be at 240 plus I sine 240 degrees. And so you just have to make sure you're aware of the quadrant that contains the complex number, and then you can decide how to get there based on that angle that you calculated. Okay, write that in polar form. Pause the video. Keep writing magnitude. It's absolute value and theta. The absolute value, 4 squared plus 4 squared, inverse tangent 4 over 4, and that gives us 45 degrees. Before we use that angle, let's see what quadrant it's in. 4, 4, and 45 degrees will be the correct angle to use. So we say Z is R cosine theta plus I sine theta. All right, so it looks pretty complicated, but all it's giving us is a radius and an angle. So if we're going to graph, we're going to rotate 60 degrees and go out 10. So if the radius is 10 and then we rotate, it'll put us right there. So there's the location of the point in the complex plane. And then to get standard form, we just have to find, we have 10 cosine 60 plus I sine 60, and we need to evaluate cosine of 60. So remember that cosine is going to be 1 over 2. Sine is going to be radical 3 over 2. And then we just distribute the 10. 5 plus 5 radical 3 I. So that's standard form. We converted from polar form to standard form. Let's go do this one. So here we have a radius of 1, and go ahead and graph this and convert it into standard form. Pause the video. So if we have a radius of 1 and rotate pi over 6, then the point is going to be right there. And then we have to evaluate it. So pi over 6, we have cosine pi over 6 is radical 3 over 2. Sine pi over 6 is 1 over 2. And there's standard form, radical 3 over 2 plus 1/2 I. Let's do the same thing with this, and we don't see this very often where there's just a number with no pi, but that's fine. Any real number can represent radians, so this just says 2 radians. To estimate where to graph 2 radians, we can think of 1 radian is about pi over 3, because pi is close to 3, and 3 over 3 is 1. So that could help us estimate where 2 radians would be. So if we're looking at the graph and we want to go to 2 radians, well, there's 30 degrees, 60 degrees, or pi over 3. Pi over 3 is about 1 radian. So we're looking for 2 pi over 3, and that means we're going to be over here. 1 radian is a little less than pi over 3, so we're going to go a little less than 2 pi over 3. And if we just make sure that we have a radius of 5, then that's where the point will be. Here we have to use the calculator for cosine of 2. Cosine of 2 is approximately negative 0.416. Sine of 2 is approximately 0.909. And then distribute the 5. And we have standard form. Okay, graph this and write it in standard form. Pause the video. We're going to rotate 180 degrees, so that'll be over there. And then we have a negative radius. So if I rotate 180 with a positive radius, we would be there. but then we have to go back to 3.5 over here. Rotate 180, reflect for the negative, and so that's where the complex number is. So 180 is here, and cosine is -1. Sine, the y value is 0, so we have I times 0. And we just distribute, we get 3.5 is the complex number with no imaginary part. And that's the end for today.